This is part 2 of the practice final for the midterm for honors chemistry, and this is one where it's shorter answer and we're really not looking at the work so much as just the answer. So first question up here has to do with measurements, and with the measurements, here are the rulers, and you can see that the rulers have markings all the way to the 10th place. So that's certain. They're certain to the 10th place, so it's our job to go one more place, so the uncertainty ought to be to the 100th place. So all measurements made ought to be to the 100th place. Well, to me, this looks like it's right on the 4 mark, and so I'm going to call that 4.00 centimeters, and it would be perfectly reasonable for you to say that's slightly more, 4.01, slightly yes, 3.99, but it should go 2 decimal places. Same thing over on the side one here. To me, that looks like it's right on the 3.5 mark, 3.5, so I'm calling that 3.50 centimeters. And again, you may say 3.51, 3.49, perfectly reasonable. Okay, second problem here has to do with those isotopes and how do you calculate the abundances. Well, this is probably one of the most complicated sorts of problems, although it's not difficult. And the basic formula here has to do with the fact that, you're going to take the abundance times the isotopic mass plus the abundance times the isotopic mass, and that'll equal 1 times the molar mass. And if there were 3 or 4 or 5 different isotopes, you would just do these terms over and over and over. Well, in this case here, it only has chlorine 35 and 37. So the mathematical trick here is the idea that we're going to say, let's say that the abundance for chlorine 35 is X, and then the chlorine for 37 would be 1 minus X. We're talking about decimal percentages out of 1. And so when we set it up, we're going to have X times 34.9689 plus 1 minus X times 36.9659 equals 1 times the molar mass 35.453. And after that, it turns into an algebra problem. So I use X times 34.9689 to get that term. Then here I split that up, so 1 times 36.9 gives me this term, minus X times 36.9659 gives me that, X, and 1 times 35.453. Now I put my like terms together, put the X's together, and put the numbers together, and I get negative 1.997X equals negative 1.51. Continuing up here in the top, okay, I just solve for X, and there's a little mistake here. This should be a negative. And when I get down, I get 0.757 or 75.76%, whichever way you want to write that. Now for the chlorine 37, it's just take 1 minus 0.757, so I get 0.2424 or 24.24%. And those are my two answers. Now, it's part 3 here is asking us to name some compounds. Well, if we're going to name them, we have to identify the type first because there are different naming rules for each one. This one we look at and we say, okay, I see ammonium and I see chlorate, so the name is ammonium chlorate. Very easy. It's an ionic compound. The second one's also ionic compound, slightly more tricky because we have copper, and copper could be Cu1 plus or Cu2 plus. But since we know that O is definitely O2 minus because we know our ions, then the copper must be Cu2 plus. So since I know it's Cu2 plus, the name here is either going to be cupric oxide, or you can also call it copper 2 oxide. Both of those are perfectly correct names. Now when you start with an H, then we know that this is an acid. Okay, so the big idea is what is the negative ion? The negative ion, that's PO3, 3 minus. That's the phosphite ion, phosphite. Now, if it were 8, it would be phosphoric acid. If it were I, it would be hydrophosphoric acid. But this ite is phosphorus acid. So remember, we put in that OR right there just to make it sound correctly. So phosphorus is phosphorus acid. Last compound here, it's I and F. They're both nonmetals, so this is a binary nonmetal compound. So it's the name of the first element, iodine, And the second element, we got to say hepta for 7. Fluoride, remember it always ends in ide. So iodine heptafluoride. Now problem 4 has to do with, we have grams and we have liters at STP, and that almost always means we're going to use 22.4. Find the number of molecules. So what's confusing about this is actually there's more information than we need. We're going to need some of it for down here for the molar mass, but 1.23 grams, that I cannot turn that into molecules unless I know the molar mass, and since we're trying to find the molar mass down the second part, that number is not going to be useful yet. So my given is really 6.28 liters at STP, and I'm trying to find how many molecules. So here's how I set it up. 6.28 liters. Okay, I can go from liters to moles, 22.4 liters per mole. And then I can go from moles to molecules, 6.02 times 10 to 23 molecules. So now I get out my calculator, 6.28 times 6.02 times 10 to 23 divided by 22.4. And what I actually did was 6.28 times 6.02 divided by 22.4. That came out to 1.69 times 10 to the 23. So I just ignored the times 10 to the 23 and saw my answer is going to be 1.69 times 10 to the 23 molecules. Now, we're going to go back and say, well, I know that the molar mass is number of moles, mass, number of grams divided by number of moles. So M over N, I'm going to call that grams over moles. So grams, I already have that. I know it's 12.3 grams, that's given in the problem. Okay, but my moles, I can say, well, 6.28 liters, 22.4 liters per mole. If I multiply 6.28 times 1 divided by 22.4, I get 0.280 moles. So if I get 12.3 grams for 0.28 moles, I would get 43.9 grams per mole. And that's how I get my molar mass. Number 5. Convert the density of copper in grams per cubic centimeter into pounds per cubic inch. Okay, so I start out by writing what I'm given here, the 8.96 grams per cubic centimeter. Now I know that a centimeter relates to an inch, 2.54 centimeters per inch, but I have cubic centimeters, so I need to use 2.54 centimeters per inch 3 times. So 3 centimeters will cancel out the centimeter cubed. And my bottom now is inches cubed, and that's what I'm trying to get. And then use my grams. Grams, I can go from grams to kilograms, and then kilograms to pounds. And I knew to do that because I'm still right here, that a kilograms to pounds, I know that conversion. So multiply all the numerators, 8.96 times 2.54 times 2.54 times 2.54 times 1 times 2.2046. Get that answer. Divide by 1001. So I divide the whole thing by 1,000. And I got 0.323697, 0.324 pounds per cubic inch. So it's a long setup, but it's actually very easy. Follow the units. One of the big problems I see is people don't use their units. They just start doing numbers and anything can happen. So follow your units. Okay, draw 2 isomers for C3H6I2. Well, the first thing I have to figure out is this like an alkane, alkene, or alkynes? They have single bonds, double bonds, or triple bonds. So remember that I's would substitute for H's. So this is going to be like the molecule C3H8, which fits the pattern CnH2n plus 2. So that means they're going to be all single bonds, no rings. So 3 carbons, all single bonds. Now I can put my iodine. Oh, I goofed this up. Okay, I need 2 iodines on here, so I'm going to change my answers while we're working. So one place I could put them both on the first carbon if I want to. And so this would actually be 1, 1 dash diiodo propane. I could do it that way. Another way I could do it would be to do iodine here. So then I could have 2, 2 dash diiodo propane. Now, This is really messy, sorry about that. So diiodopropane. Now they're all going to be diiodopropane, so I could have 1,1, I could have 1,2, I could have 1,3, and I could have 2,2. So there'd be 4 possible answers for these isomers. Now the next one up here, number 7, draw 2 isomers of C2H2Cl2. And again, I'm going to analyze first. Cl's and H's added together is 4. So that's as though I have 4 hydrogens. So C2H4 would be an alkene. That could be ethene. That's why my answers end in ethene. And it's going to have 1 double bond in there somewhere. So I'm going to draw my double bond like this. I know the bond angles are about 120. So I put my hydrogens off at 4 angles. That helps me a little bit when I get to cis and trans. So I could put my chlorines both on the first carbon, and that's 1,1-dichloroethene. And I'm leaving off my hydrogens for clarity. Again, there would not be a 2,2-dichloro, that's really 1,1. And then I could put them both on top, or I could put one down here. And if I do them both on top as I have, then that is cis-1,2-dichloroethene. Another good answer would have been trans 1,2-dichloroethene if I had put my chlorine here and here. Now the next one here, look at this picture, the structure here, and figure out all the functional groups. So for the functional groups, and I'm looking here, I see this O, and I see this O, and I see that O. And those are all between other carbons. Remember, this little line sticking out means there's another carbon there, not just a hydrogen. And so those would all be ethers. So ether is oxygen between other carbons. Then I'm going to say this big piece in the middle here is the benzene ring, and an NH2 is an amine. So I say that there are 3 ether groups, a benzene ring, and an amine. Those are all my functional groups. Now, draw the structural formula for the products when the following compounds are combined. Well, I have an alcohol, and I have a carboxylic acid, and so I'm going to make an ester, just like we did in class. Acid and alcohol make an ester plus water. Now, where do they go? This bottom little guy here is my acid molecule, and it's the O and the H that come off of here. And on my alcohol, it's the H that comes off the alcohol, although either way you do it, it's going to work out correctly. And now I want to get this little carbon here. I'm going to have that one bond to this oxygen here. So I'm going to start right here with my new formula. So H, C double bond O, H, C double bond O, and then I have it connect to the oxygen right here. And then that oxygen goes on to my benzene ring. And so just trying to copy it over, this is my molecule, and that's an ester. And water is also there. So this is write the structural formulas for the products, both products, so water is a product, so don't forget that. Okay, last part here is a little calculation with my pHs and POHs. I start off with 6.5 times 10 to the minus 7. So I just take the negative log of 6.5 times 10 to the minus 7 in my calculator, and I get my POH, which 6.187, I round that off to 6.19. Remember that since this is 2 significant figures there, 6.5, I should have 2 decimal places, so 6.19. Okay, next thing I do is I know that 14 minus my POH gives me my pH, so 14 minus 6.19 gives me 7.81. That's my pH. Because my pH is greater than 7, I run down here and say that this is basic. So as soon as I know my pH, I say whether it's acidic or basic. Then my last little section to figure out my H+, then I just said 1 times 10 to the negative 14 divided by the original number 6.5 times 10 to the minus 7, and that comes out to be 1.5 times 10 to the negative 8 molar, and that's my H+ concentration. Okay, last page. Write a balanced equation for the following reactions. Okay, propanol burned in air. Okay, a little bit tricky. Watch out for the fact that there's H's there and H's there. There are 8 H's, and also watch out for the fact there's an oxygen there. We're going to take that into account when we're done. So with C3H7OH, mix it with oxygen. Turn the C's turn into CO2s. So I have 3 of them. I get 3 CO2s. 8 hydrogens, I get 4 H2Os. So on the right side, altogether, I have 10 oxygen atoms. So on the left side, I have to have 10 oxygen atoms. I have 1 right there, so this is the other 9. So I have 1, 9 halves, 3, and 4. Or I can go back and double everything. And so I have 2, 9, 6, and 8. Both of these are correct answers. On the AP test, they do want you to not use fractions, just do everything in whole numbers. Okay, second one, a sample of solid aluminum oxide is strongly heated. Now, if we know it's strongly heated, that's not the same thing as burning. That means decomposition, and it decomposes into its elements. So first off, how do we get my compound? Aluminum oxide. Aluminum is Al3+, oxygen is O2-, and we just know that because we know our ions, plus the position on the periodic table helps us. And when we do this, we get Al2O3, and Al2O3 will turn into aluminums, and aluminums are just single atoms. And the oxygen we know is diatomic O2s. So if I have 3 oxygen atoms, that's going to be 3 halves O2, or we can go back and double everything. So 2 Al2O3s plus 4 Als give me 3 O2s. So again, the second equation would be better on the AP test. Number 12, write the balanced equation for the following reaction. Okay, so aluminum metal, so that's just Al, is mixed with cupric chloride. Cupric, Cu2+, chloride, Cl-, so CuCl2. So that's where I got CuCl2. And since we have an element in a compound, we are going to do single replacement. So the aluminum replaces the copper. So copper is going to be neutral element. And then we get aluminum chloride. Since aluminum is 3+, chloride is -1, AlCl3. Now to balance, I would balance my chlorines first. Chlorides, there's 3 of them here, there's 2 of them here. So I put a 3 and a 2. I get 6 chlorides on both sides. Now 2 aluminums mean 2 aluminums, 3 coppers, I get 3 coppers. So that's my balanced equation, 2 to 3, 2, 3. Last one, solid ammonium acetate is placed in water. Well, ammonium acetate is going to be a very soluble compound. Ammonium compounds are soluble, acetate compounds are soluble, so ammonium acetate is very soluble. So it's just going to break up into ions. I'm going to get ammonium ions, and I'm going to get acetate ions. And since ammonium is 1+, acetate is 1-, it's just 1 to 1, 1 to 1. And that's the whole part 2 of the test.